You guys have a good break? So I'll begin class with a moment of remembrance.
Oh my goodness. Draw that to go away.
I'm told the longer this goes on, the better, generally speaking. Okay, I think this marker's out. Oh, that was bad. That was really bad. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless this class today. Help us to glorify you what we do and to understand a little bit more about complex eigenvectors. Lord, in your name I pray, Lord Jesus. Amen. Sorry. You can ask Sam to explain later. So today, did you guys have a good break? So today I'm supposed to, I hope you guys have all watched the video from Friday. I know some of you had, spring break to start and stuff like that, which is fine. But I do hope you watched the video. We did, do some important calculations Friday, so you'd want to see those for sure. So today I need to talk to you guys about complex eigenvalues and vectors. They come together. And so basically here's the definition. If A is an n by n matrix, and there exists lambda in the complex numbers where, let's say lambda is alpha plus I beta, where alpha and beta are real numbers and beta is not equal to 0. Alpha may or may not be 0. It could be 0. It doesn't have to be, all right? But beta has to be non-zero for it to be a complex eigenvector, a complex eigenvalue. If blah, 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 and there exists, let's say, u equals to a plus ib, where a and b are in Rn, so u is not equal to 0. So here, technically, u would be an element of Cn. Cn is like z1 through zn, such that z sub I is in the complex numbers. So in the same way we can talk about a vector, of real components, we can talk about a vector of complex components. This is just a complex vector. All right. So u has to be non-zero, and what condition does it have to satisfy? Blah 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 blah. Where, or you could say such that a minus lambda I times u is equal to 0. If all of this is true, that makes lambda a complex eigenvalue and u a corresponding complex eigenvector. Equivalently, AU equals to lambda u, if you like, all right? So sometimes this happens to us. Like we go looking for an eigenvector or an eigenvalue, but we can't find any real ones, all right? So we have to entertain complex ones. So the quintessential example where this happens, example 1, would be something like a equals to, this is pretty much the simplest one I can possibly give you, 0, minus 1, 1, 0. All right? So like geometrically, what is this? This is a what kind of matrix? Do you guys know? So like something you should know about, if you think about the matrix cosine theta, sine theta, minus sine theta, cosine theta, this is a a rotation matrix, right? And we've played some with these other days. We'll do more with them again, but this is a rotation matrix in the plane. And so this is apparently a rotation matrix for what angle? 90 degrees, right? So if you think about that, if you think about taking a vector, right? Take a vector based at the origin, let's say, right? And you rotate it 90 degrees, right? You rotate it 90 degrees. It doesn't matter where you start. If you rotate by 90 degrees, you're not doing this, are you? You're not doing the vector as a scalar multiple of the vector in the real sense, right? So there's no real eigenvector to this matrix. We can see that from geometric principles to start with, right? So what's the deal then? Well, it turns out it has complex eigenvalues and complex eigenvectors. So here we go. Let's look at it. So by the same theory we already did, like theorem, the determinant of a minus lambda I has to be equals to 0, all right? That theorem for lambda being an eigenvalue is still true. All of the eigenvalues which exist out there, they have to come to you from the solution to this thing, which is called the what? This is the so-called characteristic equation, right? And the thing is about the characteristic equation is it is a nth order polynomial equation, right? If it's an n by n matrix, you have n copies of lambda in determinant a minus lambda I. So when you multiply it out, you get an nth order polynomial. What's the story for nth order polynomials? What kind of solutions do you have? If it's a real polynomial with real coefficients, you either have real solutions, possibly repeated, or complex solutions, possibly repeated. There's nothing else, right? So like the fundamental theorem of algebra tells us that this equation will have n solutions if we use complex numbers, right? Possibly repeated. So if we take a complex approach, we know that there will always be n eigenvalues, again, possibly repeated. The question then is, like, how does that fit into the story of diagonalizability that we started last, Friday? Like, how does that fit, and what do we do with these things? So I'm going to show you that today. See here, so let's find it. So we've got minus lambda, minus 1, 1 minus lambda, if I do my a minus lambda I there. And that gives me lambda times minus lambda times minus lambda is lambda squared. So you get lambda squared plus 1. You set that equal to 0. This tells me that lambda is always equal to, well, plus or minus I. These are my eigenvalues. In this case, the eigenvalues were pure imaginary. All right, pure imaginary. Now, great, so let's find the eigenvectors. So let's put lambda equal to I. Then we'd be solving a minus II times u is equal to 0. Specifically, that looks like what? Let's see here. So we've got minus I minus 1, 1 minus I. And I should maybe call it u1. I'll make it, uv is my disposable variables as usual. Okay? Like we did last time? Last week? Wait a minute, not last week. Who knows what you guys are doing last week? What did I do last week? I did something. Oh, that's right, I plotted against a different class, not you guys. So, anyway. Oh, and I painted a room. I thought about doing other things. I didn't really get anything else done. And my son shaved several hundredths off his time in swimming at the regional meet, so that was very exciting. So swimming is nuts, by the way, guys. If you have children, keep them out of swimming. It's a lot of work for you. Generally, sports are evil. Keep your kids out of sports. Just saying. All right, you're here, you're nerds. It's good advice for you. Let's see here. So I'm mostly joking, or am I? I don't know. But the thing is, these look like different equations at first glance. So if those were genuinely different equations, we'd just get one solution, which would be what? 0. 0 would be the only solution. If these are distinct equations, they're both homogeneous, they go through the origin, if you think about them in that way, the solution would just be 0. But that can't be the case, because if 0 is the only solution, it's not an eigenvector. But good news, if you multiply the bottom equation by minus I, what do you get? Oh, wait a minute. Whoa. Dude. Oh, I'm an idiot. So if let me actually write it out. So we have u minus iv equals to 0, right? Multiply this by I. What do you get? You get I, minus I rather. You get minus iu plus I squared v, which is what? So my point to you is that when we do these problems, we should see that one of the equations is just the other equation. If it's a 2 by 2, it must be that they're the same equation. Or the other thing that can happen is one equation can be like a thing and the other one can just be zeros, right? But either you need a row of zeros or you need one equation to be the same as the other, because otherwise we'd only have the 0 solution, right? And we can't just have the 0 solution, because the theory we talked about before break says if you get one eigenvector, you have to have infinitely many, right? Because I can always take this equation and multiply it by a constant, and I still have the same equation, right? Like, see this? I can just put a c here, if you can fit it in there. C times u, and it satisfies the same equation, right? So if you got one eigenvector, any scalar multiple of that will still be an eigenvector. And now I'm talking about complex scalar multiples. Okay, anyway, so good news, these are the same equation. They just kind of, at first glance from our real perspective, they seem like different equations, but they're not. So it doesn't really matter. You could take either one and solve for the variables. I personally like the second equation. Second equation gives me u is equal to iv, all right? U equals to iv, and so I can just set u equals to 1, then v, put v equals to 1, right? Put v equals to 1, then u is equal to what? I, right? But the truth of the matter is, like generically speaking, u1 looks like what? It looks like, let's see here, iv, v, where v is a complex number, v not equal to 0, right? So this is the generic form of a complex eigenvector here. So these problems are especially annoying if you're working and checking answers with other people, because how many different choices are there for v? Anything non-zero in the complex plane works, all right? And choosing different complex values for v corresponds to like really different looking answers, but they're all actually the same in their application, which we'll talk about in just a moment. Okay, so here we go. So anyway, basically we could say W1 in this case is the span of, what's my vector? I got I and 1, all right? So this is the lambda equals to I eigenspace, for what it's worth. I don't talk about that one too much in this context, but just to be consistent with my earlier discussion. Something really, really neat here happens. Now, when we were in the real case, if we had distinct eigenvalues, what do we have to do? We had to work out the equations for each one, right? In the complex case, there's a beautiful little theorem that we should work out. And I guess I can do it here. I'm going to erase this, okay, guys? I'll probably regret erasing what I just erased, but anyway, did what I did. So if you have AU equals to lambda u, then we can complex conjugate. Complex conjugation. So we have AU star is equal to lambda u star. Now what does complex conjugation mean? I don't know how much. Have you guys had like a course in engineering where you had to use complex numbers at some point, or am I just completely blowing your mind at the moment? How much do you know about complex numbers? Do I need to like spend 10 minutes talking about what is a complex number? No? Okay, cool. See, because the definition for the complex conjugate of a matrix, the ijth component of that, is the ijth component of the matrix complex conjugated. So like complex conjugation is just done component-wise. All right? And properties of the complex conjugate are stupidly simple. So like the way this works is A conjugate, U conjugate. It doesn't even do the sock shoes things. It's just this. All right? Where what I mean by that is we're talking about the component-wise complex conjugate of A. Lambda is just a number, and U is a vector. What did we say about A, though? This right here, right? How do you say a complex number is real? What equation does it have to satisfy in terms of complex conjugation? If I take a real number and I complex conjugate it, what do I get back? Hey, you guys told me you knew complex numbers. Yeah, what? The same number, right. So if A is a real matrix, what do we have? Let's have A again, right? Because every number just conjugates to itself. So we get A U star is equal to lambda star U star. What's that say? That says, aha, U star, which is A plus IB complex conjugate, which is what? A minus IB, because A and B we're assuming are real numbers, right? So the complex conjugate of a vector can be just done by switching the I in the middle right here, right? Flipping that I to minus I, because A and B are real. That's how complex conjugation works in this notation. And so what does this mean? Well, this means that U star is an eigenvector for A with eigenvalue what? So like lambda star, right? In terms of the alpha beta, that would be alpha minus I beta. So for my example 1, I don't need to work out the lambda equals minus I problem separately, right? Other eigenvector for lambda equals to minus I, right, is U1 conjugate. So if I use my, I1 and I complex conjugate that, I would have like minus I1. All right. Any questions? All right, so we could do various things with this. So we talked about diagonalization, right? So one thing I could do is I could say, okay, so I'm going to let beta, and so this is unfortunate. Let me not let beta. I'm using alpha and beta for like the scalar components of the eigenvector. I better use some other letter for the basis. I guess I could use gamma. Let gamma be I1 and then minus I1. All right, that's a basis. It turns out that that is linearly independent in the complex sense. And so if you calculate the inverse of that matrix times A times the matrix gamma again, then by the same arguments that we went through in the real case, that will diagonalize the matrix. All right? And in particular, it will diagonalize the matrix into a complex form. In particular, it's going to give you I, 0, 0, minus I. So you could call this a complex diagonalization if you like, I suppose. So most people, I could put some quotes on that. Most people wouldn't count this as a diagonalization of the matrix, because in most contexts we have to keep it real, right? So while this is interesting, it's not really what we're after for applications. But it does have its place, logically speaking. Right? Do you guys know how this calculation would go? What would gamma inverse be? Like how, I hope you know what I'm talking about, right? Like we just make that 2 by 2 matrix. The inverse formula still works for complex 2 by 2. Everything we did for real matrices still works for complex matrices. Because we haven't really done anything with inequalities, right? Less than, greater than. That's the thing that fails for complex numbers. We're not using that here at all. It's just equality properties of algebra. Those things are still true for complex numbers. Anyway, so there's that. Now, I guess I'm going to leave that for now. Let's do another one. There is an application of these things to the study of differential equations, which I'll talk about before today is done, I hope. We'll see, though. This one, I don't know how long this is going to take. I just copied this out of the book. This might be your homework problem. I really don't remember. I didn't double check. It could be. It may not be. I don't know. You also don't know since you haven't done your homework yet. Guessing. But I don't know if you haven't or not. Let me not put that on you. So but I do know this. I copied this out of the complex eigenvalue, eigenvector part of Ley. So ostensibly, this has complex eigenvalues and eigenvectors. So let us suffer together and try to solve this problem. I mean, what am I talking about? It's not suffering. It's pure joy. Let's see here. So the determinant of A minus lambda I. So I think pretty much all of the examples I've worked in class up to this point have shielded you from the real difficulty of calculating the determinant. Because by some method or another, the determinants that we've looked at have like factored nicely, and in the wild, they can be kind of a pain. So let's see what happens. 2 and if you don't like lambda, you could use x for your variable here. I would not be offended, as long as you don't confuse that x with the x that we also use for the solution to the eigenvector, which I've seen students do. But you guys wouldn't do that. You're better than those students, because they're not here. And let's see here. So I'm going to factor a minus out. So that's minus lambda plus 8 times the determinant of this guy right here, which would be lambda minus 1 times lambda minus 5 minus 24. There was an m by this problem. I wonder if that means anything. 12 times 2 times 5 minus lambda minus 14, and minus, let's see here, minus 6 times the determinant of this guy, which is 24 plus lambda minus 1 times 7. Now, I try to avoid writing minus lambdas when I actually multiply the determinant out. So what I do is I factor out minuses and think about minus times minus being plus in my head as I write things down to avoid a preponderance of minus signs. I don't know, like, you got to do what you got to do, but this is how I did it. Now, what are some things we can look for? What should we expect about the factoring here? So one thing we should expect is that the trace of A is equal to, well, we know it's equal to what? 6 minus 8, which is what? Sum of the diagonals is what? Negative 2. All right. Theory, that's the sum of the eigenvalues. This is a theorem. The trace will be the sum of the eigenvalues. So that's something you can kind of think about as you're double checking your work. The determinant of A, let's see here. right, so if you think about this, this is going to be what, like minus lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3, right? Like when you work this out, that's what has to happen here, because there's 3 lambdas, so if we multiply that out, the leading term is going to be like a minus lambda cubed. You can kind of see it right here. So that's there, and when we factor it, it looks like that. All right, so if you think about putting lambda equals to 0 here, you get the determinant of A, right? So I also know that the determinant of A, I think, should be equal to minus, so apparently the product of the eigenvalues. All right, so these, fun facts. I don't know if that's going to help us or not. It's just something there to look for. Although calculating the determinant of this matrix doesn't seem particularly easy either. Yeah? Did I tell you guys about the calculator? So I don't know if I've had this talk with you guys yet, but it has come to my attention that this innocent-looking little non-graphing calculator has a convenient and, in fact, useful interface for entering matrices. I can put a 3x3 matrix in here. I can calculate its determinant with a push of a button. As such, I'm now going to allow graphing calculators in this course going forward. All right. Or you can use this. The alternative is for me to ban all calculators, but that seems kind of draconian. So if you'd like, I can show you how to calculate the determinant on this. Would you like guys like me to make a video of that? I could do that. I meant to do that over break, but it's not that hard. And for shame, I haven't figured that out already. But it's in there. And I think it's in older versions of the calculator too. Although I can't be sure because a student stole mine last semester. He did give me a gift card for $25 though, so I felt better. Although I don't think that was the reason he gave me the gift. Anyway. So have you guys worked it out? All right, so let's try it out. So I've got minus parentheses lambda plus 8. All right, so we've got lambda squared minus lambda minus 5 minus 6 lambda. I've got a plus 5 here, minus 24, which is a minus 19. And then over here, I've got 24 times 5 minus lambda. Let's see here. Plus 12 times minus 14. Minus 12 times 12. Minus 42, of course. Lambda minus 1. So what do we get? Minus lambda plus 8 times lambda squared minus 6 lambda minus 19. I've got 10 times 12, and then I've got I believe I have a total of, I should just use my calculator, that's wrong of me. Oh, these are both negative. So that gives me minus 26, minus 36 times 12. I think I maybe got minus 36 times 12. Am I wrong? What's the constant term in all this, ignoring the first term? Am I on my own up here? Is that right? Let's see here. 5 times 24 is 14 times 12. Minus 12 times 12. Plus 42. So I get a net of minus 150 from all those constant terms. And we've got a minus 24 and minus 42, I believe. So I get minus 66 lambda. All right. Great. So I've got a minus lambda cubed plus 6 lambda squared plus 19 lambda minus 8 lambda squared minus, plus 48 lambda minus 8 times, let's see here, what is that? 8 times 19. I got a plus 152. So that, what I did was I just distributed the minus lambda times that, and then the 8 times that, minus 8 times that. Watch my signs. All right, okay. And then, of course, I still have the minus 150, minus 66 lambda. For something like this, I have found that pretty much the only way to go, unless you can just, if you're so fortunate as to see a common factor between what's over here and what's over here, then you can just factor it out, and then lovely, that's great, that's wonderful. I just don't see it. It may be there, I just don't see it. I mean, it probably has to be there, actually. Logically speaking, this has to have a what? You have a real cubic. What must be true? What does the graph of a real cubic look like? Like a snake, right? Or up, down. Anyway, the point is, it has to have a real root, right? Every real cubic equation has a real solution. At least one. Now, since I got this out of the complex eigenvalue section, I believe in my heart that the other solution's complex. Right? So what is it? I don't know. Is the real root pretty? I don't know. Let's simplify this. So I'm going to factor a minus out because I can. And I got a lambda cubed. How many squares do I got? Plus 6 minus 8, which gives me minus 2, which gives me plus 2 lambda squared. Linear terms. Here, here, and here. Them's my linear terms. What do I got? 48 plus 19 minus 66. Oh, 1. So that's right, there's 1. So I factored a minus out, so I can make that a minus lambda, right? And then, what's that? 152 minus 50 is 2, but I factored the minus out, so minus 2. All right, so apparently the determinant of this matrix is 2. All right, if you believe this calculation, we could double check it. Any thoughts on what the eigenvalue might be here? What could you try? When I get to something like this, a 1, does a 1 work? If I plug 1 in, I get 1 plus 2 is 3 minus 1. Yeah, 1 works. So I'm going to switch back to x because I do better. So suppose you've got x cubed plus 2x squared minus x minus 2. Let's factor out a x minus 1. So that gives me x squared, x cubed minus x squared. That gives me 3x squared minus x minus 2 plus 3x. So I've got 3x squared minus 3x. That gives me 4x. Wait a minute, no. That gives me 2x minus 2, which is, thankfully, 2. Gives me 0. Dudes, seriously? Not cool. Oh my goodness, I am so annoyed. All right, so that's apparently lambda minus 1 times lambda minus 2 times lambda minus 1. Great. Wonderful. This factors. Well, I got this out of the complex eigenvalues section. Lay, I'm not happy with you today. This was supposed to be a complex. This was supposed to be a complex eigenvalue example. It is not one, though, is it? Is it? What are the eigenvalues? They're all real, right? So, yay. But this is not what I was trying to show you guys today. Oh, good grief. So sorry. Yep.
Maybe I'm just not seeing your stuff. But
Oh, did I make a mistake?
I see a 2x squared minus x squared, and you got 3x squared.
Oh.
And you're subtracting.
Wait, where? There's hope? Where'd I do it?
The 2x squared minus x squared, and you got 3x squared, like your first step.
Oh, but this is long division, so like,
Oh, I see.
I mean, it did work out to 0. So I would have to be making a slew of errors to get it to all, gel like that. Let me double check right quick with the eigenvector calculator. Can you guys read the matrix out to me?
-8, -12, -6, 2, 1, 2, 7, 12, 5.
Yeah, real eigenvalues, -2, -1, and 1. Oh, I did at least mess that up. All right, so you guys told me 1 was the eigenvalue, but this one has -1. That puts a, I should, yeah, minus, these should be pluses here. My bad, yeah. Plus, yeah. So like, this would tell me lambda 1 equals 1, lambda 2 equals -2, and lambda 3 is -1. The numbering is not important. And then we can do the calculations we did last week to find out the real eigenvalues, eigenvectors. All right, but I don't want to do that because we already done that. Okay, I have no regrets. It was good for you to see this. Like, we should suffer together and calculate a hard determinant. Now we've done that. It's just not what I was trying to illustrate today, so I'm annoyed. Give me a second here. I will redeem. Just change a number. Just like. All right. Well, I just have to accept it is what it is for today. But I will find an honest to goodness 3x3 complex example for tomorrow. Let me spend the rest of the time talking about the application of this and another calculation we haven't done yet. So, sorry guys. And this thing we're just erasing right now, this is the hardest part of this material, like for sure. Actually, being able to do that calculation with confidence on a test is a high bar that some of you will probably reach. But I do give partial credit also. So, I mean, it's hard to get that one right. There's a lot going on there. All right, so let us talk about a little bit more theory. So here's a theorem. If we have, u equals to a plus ib with, complex eigenvalue alpha plus I beta, beta not equal to 0, and AU is equal to lambda U, then if we look at the A and B, this is a linearly independent set. So and also, among other things, that means that both A and B are not equal to 0. It's more than that. Like the real and imaginary part of a complex eigenvector, they cannot be linearly dependent. All right, this is proved in the notes. I won't do it here. But so that's useful. See, because let's think about this. We had, before we proved that dx dt equals to ax has x equals to e to the lambda t times u, the so-called eigensolution. Remember that? Well, it turns out all of the calculus we've done, it still works. It still works just the same when lambda is complex. Like when lambda is complex, e to the alpha plus I beta times t still makes sense when it's complex. This is what this means is e to the alpha t times e to the I beta t. All right? And e to the I beta t is the sum of sines and cosines. In particular, this is e to the alpha t cosine beta t plus I times the sine of beta t. This is called Euler's formula. Maybe you derived it in calculus too, maybe you didn't, but this is something that's true and important to know about. So a complex exponential is a product of an ordinary exponential and a sum of sines and cosines as appropriate. The neat thing is, if we look at our solution in the complex context, all right, so we've got like e to the alpha plus I beta times t times u plus, times a plus ib. All right, so here's my complex eigensolution. Let me call it z. All right, the complex eigensolution. What does this actually look like when we multiply it out? Well, what we have here is we have e to the alpha t cos beta t plus I e to the alpha t sine beta t times a plus ib. And multiply this out, we get what? We get, I'll factor the e to the alpha t out because it's everywhere. So we get e to the alpha t times cos beta t times a minus sine beta t times the b vector. And I'll factor an I out here, plus I e to the alpha t times sine beta t times a plus cosine beta t times b. So this calculation I've just done is, well, all I'm doing is I'm taking the complex eigensolution, I'm expanding it into two pieces. This is what we would call the real part of z, and this over here is the imaginary part of z. Man, this marker really, really stinks. It smells like something dead. Not in a good way, you know? Barbecue. So, like, the theory is pretty simple. If you have z is equal to, say, z1 plus I z2, and these are like functions of time, then dz dt, the calculus is just this. It's like dz1 dt plus I dz2 dt. So in other words, to differentiate a complex valued function of time, you just differentiate each component, which basically means the I just rides along and you differentiate like normal. So if that's the case, think about this. If you have dz dt is equal to az, right? Then this becomes dz1 dt plus I dz2 dt. And this, on the other hand, becomes az1 plus I az2. All right? But the thing is, that's a complex vector equation. The only way that can be true is if separately we have this is equal to that, and also this is equal to that. So complex, the merger of complex and real analysis is just, it's just too nice. Every time we get a complex solution, we get a pair of real solutions. One complex solution begets us two independent real solutions. These are those in detail. For the complex eigenvector, we get this is a real solution, and that is a real solution. So in the case of a, like this problem, example 1, so for example 1, the way this plays out is to solve, if I'm solving dx dt, well, let's say, I guess I can write it out and let me go back to scalar notation for a second here. So the differential equation we'd be up against would be something like dx dt is equal to minus y, and dy dt is equal to x, right? That would be the corresponding system with this matrix, right? That if you write that out as a matrix, it's 0, minus 1 for the minus y, and 1, 0 for the x. That has this coefficient matrix, all right? And so what I'm saying is that the solution, xy, can be written as c1 e to the, like this, all right? But what does that actually work out to here? So in this example, we had what? We had, a equals to 0, minus 1, 1, 0. We found that lambda was plus or minus I, right? So I'm just going to choose lambda equals to I, identify alpha equals to, wait a minute, not 1. Alpha is equal to 0, beta is equal to 1. All right? And so for that example, I have, so what's e to the 0? Yeah, e0 is just 1. And so we're just, and beta is 1. So we're just looking at cosines and sines. So we've got like c1 times what? Times cosine t times a minus sine t times b plus c2 times sine t times a plus cosine t times b. Now the question is, what are the a and the b? But for example 1, your u was, what was it? It was, well, we chose it to be what? We chose it to be I1, right? So you can rewrite that as 0, 1 plus I times 1, 0. So what we've got here is c1 times, well, a is 0, so this is my a, this is my b. So I get cosine t times 0, 1 minus sine t times 1, 0 plus c2 times sine t 0, 1 plus cosine t 1, 0. And that is the solution to the differential equation. So in the case of a complex eigenvalue, we find the complex eigenvector, and then you find its real and imaginary parts and do this calculation I just did here. Like, you can just memorize these formulas or write them down in your card or whatever. I don't expect you to have to work all this out. You can use, this is basically a theorem we're deriving for you guys. Like, this is what we do. We take the e to the alpha t times cosine sine like this and like that. And that gives us the solution. And there it is. Anyway, more tomorrow. Sorry about the middle example. Ay, ay, ay.